Well, first of all, I'd like to thank Google for the opportunity to share some of the work we've been doing around R and C++. On a personal note, I've been using R for so many years now, for about 10 years, and the joke I usually say now is that it almost feels like I'm married to language, to the R language. I keep having fun with the language. I keep learning new things about R. I keep being really interested in this language. Although it doesn't mean though that I don't often like to spend time with other languages. Having a few indiscretions with other sorts of languages. I've had a long-term story on the side with Java. We're not talking too much to each other anymore these days, but this was a nice relationship. So when Dirk introduced me to C++ last year, I really spend a lot of time now with C++, and I'm really happy to have learned this language. And now what we want to do today is share some of the work we've done and show this indiscretion. Obviously, Dirk has spent much more time than me over the years with C++. I've just started a year ago, but we've managed to do quite a substantial amount of work since then. And so this is what we want to share with you today. Okay. Julien?
Yeah, let me just briefly share what Romain said and say thank you to Google for having us and Murray for making this happen. This is really nice. We're sort of going to talk about R and C++ and connections in a large sense. The bridge that was on the previous example will come again as a metaphor, and here's just a few points, sort of what we're assuming. So, generally speaking, everything should work with current packages on all supported operating systems. Exceptions noted. So we didn't have a protocol buffer binary on Windows. That's something that we may sort out. And some of the most recent slides assume the version of R that was released last week. And also we made shortcuts and things. So just then as an introduction, we weren't quite sure who we'd be talking to. Experienced long-time R users or otherwise computer scientists interested by R. So, just to get warmed up, here's a really simple example on why you would want to work with R that crossed sort of my daily readings. That was on the mailing list the other day. And in the beginning, it's just sort of three statements. Sort of we assign from one of the given data sets. There's sort of a bit like a running joke that in R, many things are on standard data sets. So eruptions of the faithful volcano are 1. So we're just assigning those. We're fitting a density function, and we plot those with 3 standards. Nothing special about that. But the actual example that was shown was the following. So with just 4 more statements, you get a Monte Carlo replication over 10,000 repeats of estimating this density, then taking quantiles out, and hence seeing the uncertainty around that density estimates as well as the fit itself. And that's why we keep using R, because it's not that easy to do this in 7 statements with another language. So with that, let's sort of take R as a given, and once you work with it and are curious about pushing it a little, you think about extending it. So that's how we got here, sort of extending it via C++. Extending R is covered in 2 chapters in John Chambers' most recent book, and that sort of really spoke to me when I first read that. So I just want to highlight what he said here, which is, it's R itself, the interpreter is the C language program, so you can extend it easily from C, but it may not be as easy as it seems. So he says there are some added dangers, and there may be a substantial amount of programming and debugging involved. So he then discusses this a little bit more and puts a roadmap up with a couple of points against. If you do this, it's more work than programming in R. If you get bugs, they will be nasty. If this may introduce potential platform dependencies, and your code may be less readable, may or may not be. However, if you do this, you can go and into uncharted waters. There's the directive and the mission, of course, all throughout the book. So you can boldly go and try things that haven't been done before. You may also just reap speed. And there was something already about object references. We'll come back to that, but basically one of the two extension paradigms in R made that relatively easy. So, you know, I grew up with a lot of soccer around me. If I look at that, it's a score of 4-3 towards the end. So it's the deck stacked against us. Should we do this or should we not do this? And what we're going to do with this talk is to convince you that absolutely you should do this because you pick the half that you're playing in, and we hope to convince you that with sort of some of the tools that we've worked on, it gets a lot easier. So remember from the opening slide, there was a bridge. Bridge as a metaphor to get from one language to the other, and that bridge, we'll come back to it briefly, is sort of a dangerous bridge. What we are sort of trying to think is that, you know, the work that we're putting together, of course, it's not quite as impressive as Norman Foster's work, but it's more sort of along the lines of this. And this is actually something relatively close to where Romain lives in Montpellier, and it shaves an hour or more than an hour of his travel time. So, you know, it gets you different places, it's well engineered, it's safe travels, and a lot faster. So works for us. So what are we going to talk about? It's mostly about Rcpp and a couple of other projects that came along with it. The goal is to make the integration between R and C++ easier and more seamless. This uses a standard interface in the R system, the .call interface. On longer talks, I sometimes mention also the preceding ones, but let's just work on this. And basically, it operates on a standard union-style data structure on inputs as well as outputs. We do come back to that. What Rcpp offers then is a natural mapping between objects in sort of the programming sense between R and C++ using C++ classes. We've also did some work that helps tremendously for prototyping using a package called inline, work by somebody else that we've extended to use it in this context. It's also heavily used by us. We have over 700 unit tests in the package, and they basically all use inline. We'll show how that works. This puts no additional hurdles and burdens on you for package building. And, you know, some extensions that came along help with other things like highly efficient math using other recent C++ tricks. And I think we'll come to that as well. Shall we split? Or why don't you do a turn? So.
Okay, so essentially what Dirk said before with the other slide is that there is an existing bridge. I mean, R already lets you connect to C or C++ out of the box, but we feel that to be able to cross this bridge, you have to wear a nice fedora hat and have a whip. And well, not everybody, you know, does that. So we believe we can make a better bridge there. So this is sort of a comeback from previous slides. So R is a C program. And so quite easily lets you augment R with other C extensions, and it easily extends to C++ as well. All you have to do is include a .cpp file in a specific place in your package, and you're able to use C++. But you do this through a C API, which is essentially you know, C functions and macros, and we believe we can encapsulate things much more nicely and with what we've done with Rcpp. So the sort of function we will see here are functions that all look the same. They take 0, 1, or up to 65 R object. Any R object is SEXP, and they return another one. And to be able to call them, you do .call, the name of the function, and then you pass arguments to it. So that's the classic sort of how to call a C or a C++ function from R. And then the sort of things you do is, I'm not sure everybody can read this, but Yeah, you see the sort of C API you're able to manipulate there. So we get A and B from R, the two parameters of this function, and then we sort of carefully coerce them to numeric vectors on the fourth and fifth line with the protect statement. Then we create a new numeric vector of a given size that that is the size of the A object. Then we grab the actual data pointer, the double pointer, and then we manipulate this to do some really simple computation there. The sort of thing I probably want to highlight there is the protect. When you create new objects, you need to protect them so that the garbage collector doesn't come and steal them from you. And then when you're done with these objects, when you want to return back to the R side, you need to unprotect them. Right. This asks a lot of work from the programmer, and we believe we can do nicer than this, and well, we know we can do nicer than this. So some other example to manipulate character vectors. So you'd have to, again, protect. You'd have to call a log vector to create a new a character vector of two strings. And then to set the strings, you call another macro, set string element, the object position, and this funny mkcar function again, and so on. So this is typical C examples you use when you extend. Yes. Yeah. Whatever. Another function. I'm not even going to talk about this too much, but what if you want to call an R function directly from C? Well, you can do things like this. It makes Lisp people really happy, but it makes me, going to the pharmacy too much. So there you go. That's the kind of examples of C code you can embed in an R package if you don't have Rcpp. And if you do have Rcpp now, well, this is what we'll talk now. Do you want to?
So just to summarize, what we're offering is encapsulations of these S expression objects. That's a union type, and it's the thing that gets passed no matter what is represented as something you generated in an R session, R program. We represent those then as vectors of numerics or ints, as a function, as an environment, language, lots of them. There's two very important worker functions, S and Rep, which help you to go from R. The wording is still wrong. So S actually it's the other way around. It's from C++ to R, and it's Rep for sending it back. And the way we've set the classes up, it also cooperates quite nicely with current programming standards. It uses a lot of things from the STL like iterators. So here's a bit of a long table. Won't stay too long on it, but basically what you have on the right you may know as an R programmer. There's integers, numerics, logical expression, characters. There's more advanced things that you may have used. I once worked a lot with external pointers to overcome some memory limitations. There's S4 classes, functions, environments, all that. We have that. If your R script has one of these, you can pass them down and you have them in C++ and you can work on them. That's a good thing. Just a quick example about how this works. There's different ways to go about the business. We don't prescribe a single one. So suppose that you've gotten through .call or otherwise an S expression X. You can immediately use a constructor from an SEXP to create a numeric vector Y of X. A really important point that we'll be coming back to is this tests for type. The SEXP is a union type, and it could be anything. So you could be writing down a function and want to construct a numeric vector from it. That won't work, and that gets called properly. I know that your programming guidelines sort of argue against exceptions. We found it helps us for sort of cases like that. That may be a point where you guys need to differ in the code if you want to avoid that. Other things are deep copies of the objects. We're using what sometimes is called proxy classes because these R objects really are pointers. We're having relatively shallow and efficient wrapping around them. So if you're not careful, and we had some examples like that on the mailing list, if you create two objects, they're actually not distinct. If you want the same sort of content twice, you have to use clone. That's common with some other C++ frameworks too. So in essence, we offer a deep copy. You can also, of course, construct just from a numeric. If you just give 1 for vectors, the semantic is then, oh, you want a vector of that size. Likewise, you can also create of that size and have it filled. That works if you have a numeric vector, which by its type is constrained to be of a single dimension. If we give 2 arguments, that's interpreted as size and payload. You can also have sort of an internal sweep, if you wish, over it and have it filled, for example, with uniform randoms. What happens is you see sort of : RF there. R itself, C API, C header files. Over the years that I've used it, I've often combined it with other software that may have other header files, and R is a little generous at times about what it defines in macros. There are things like lengths, max, and you can run into accidents with that. And the best way around it, there is, of course, everything can be done with R. There's a way around it, so you just basically have to define no remap, which we do for you. But the consequence of that then is that you need to basically explicitly, the way it's done in C, prefix your namespace with rf underscore for all functions. So instead of having lengths that may conflict with somebody else's lengths, now you have rf underscore length. So this fills you with the uniform, and then likewise you can also use the : create. That's often used when we return from functions to have existing options basically just placed in there. We showed you other examples, character vectors, how to call a function. Here's just something that we hadn't shown at the R example, but environments are something very important for advanced sort of R programming. There's a few constructors for environments that your R session will already have: global environment, empty environment, base, and so on. You can create new environments. You can inherit them from existing packages. You can refer to parent and child environments. So it's basically what you may need to encounter is provided. Here is an example from, I think, the first user package that I had when I started working on this again after sort of the rebirth of Rcpp. That's from someone in South Africa who wanted something really simple. He just wanted to create a new distance metric on vectors. And he had a C++ function that did that and came to rhelp or rdevel and didn't quite know what to do. So I told him, well, there's this package that makes that really, really easy. And at the time, there weren't that many other existing packages to point to. So I just gave him a hand. And it's still only in RForge and not on CRAN because the underlying C++ function, I think, has a corporate copyright from Siemens on it. And with that, it's not sort of really open source. So we didn't feel like it's worth putting on CRAN, but we may. I put that up here to show that if you have something that wraps, say you have a certain library function somewhere and you want to bind them, this is sort of the minimally sufficient framework. For this particular function, earth moving distance, L1 measure, there's sort of 2 vectors in there. It computes the distance between the 2 and a sex for parents. The way it's used then is that you instantiate the 2 vectors. That's very straightforward, just as we did on the previous slide. Then there's also params, which we stick on a list. And this slide sort of works as a reminder what lists can do. Lists are our, catch-all, for all purposes data structure in R. It's the one data structure that can contain lots of different objects of different types, and it allows us basically to do key value lookups. So here we're then just looking for a parameter that should be passed in an R list, parameter called verbose, which we expect to be a bool. An exception will be thrown if that's not the case, and with that we can just assign it to bool. You could have 1, 2, or 2 dozen such lookup parameters, and it also allows nesting because lists can contain lists. Basically, it's a data structure that is a list of SEXPs. Each element can be an SEXP, so we could also have passed those 2 vectors inside that parameters had we cared for it, but that's obvious. The same thing happens when you return. So here we're using the create member function for numeric vector to send the distance value, which is actually at that point a scalar, I believe. So we could have sent a double per share with the named with the name dist back. So it's a vector that you can use named lookup on SNR. And at the bottom is the standard framework to catch exceptions of that inherit from standard exceptions. And then the text gets passed back, and you actually get that at the RPront. Or if it's an unknown exception, you just get a stanza. You want to take from here? That leads to Sugar, I think.
So some other example, I'll quickly go through it because we have a lot more things to cover. This is the same example that we did show before with the macros. So as you can see, with their the code is much shorter, and then we can use larger font so that you can actually see what's happening. So what are we doing? From the SCXP we grab from R, we create numeric vectors objects from Rcpp, and then we can start using them. So we can grab the size of the object with number of elements in the vector, create a new vector of that size, and then it's just regular sort of C++ business. I mean, we grab each element from each vector and then do some really simple computation there. As you can see, there's no more macros, there's no more protect and unprotect. The Rcpp API takes care of making sure that your object is protected when you create it, and then just relieved to the garbage collector when it's no more needed. So for this we use the regular sort of C++ life cycle, and it makes code much more easy to write and debug, and well, it makes it a bit fun to use as well. So some of the examples there. So creating a list. So imagine you have a std vector from some other library you get, and you want to return a list to R. So a list that will contain the first item will be a numeric vector of 2 objects. So a numeric vector create 1, 2. And then the other one is integer vector with one element, 3, and then a string, and then the vector. And all of that makes it really easy to create data structure that you can just ship back to the R side with a really nice syntax there. And then you can assign a class to it, whether you want to use a S3 object, and then return the object. I mean, if you wanted to write the same code with the R classic sort of C API, you would have to use a much smaller font to be able to show this on the slides. Some other examples. This is an example that came fairly recently on the mailing list. It actually came on the R help mailing list, but someone picked it up. Well, Doug Bates picked it up and sent it to us on the Rcpp mailing list and said, "Well, can we do something about this to make it faster on the Rcpp slide?" So we had a go at that. So the idea is that we want to go from the first matrix to the second one, which, well, for people familiar with apply and CumSum, this. So the second column is the sum of the second column of the output is the sum of the first and second column of the input, and the third one is the sum of the first, second, and third column. Yeah, so you get the picture. So in R, if you want to write this in R, you go either using apply, or you can do it directly using a for loop. Turns out that the for loop is quite an efficient way to do it on this example, as opposed to what I initially thought it would be. But can we do better using C++? That's the function we ended up writing. So we grab the object as a numeric matrix. As Dirk pointed out before, when we create a matrix, if it's not a matrix on the R side, then this will not fly. This will throw an exception and let us go back to the R side. But then here we know it's a matrix. And then we grab the number of row, number of columns of the matrix. We clone this matrix to create the result. And then we can then just scan the matrix. So the current column is then the sum of the previous column and the current column of the input. So it makes really straightforward sort of vectorized code in C++. So does it actually make it better in terms of benchmarking? It turns out it does. Well, when we started working on these slides a few days ago, the version I had was not better than the R version, and so we've been able to do some work there on optimizing things. But yes, in that example, the C++ version turns out to be faster, not by a big margin, but we have other examples where the margin is quite more impressive. STL is a fairly used library in the C++ world. All of our data structures, vectors, lists, all expose STL sort of interface. So we'll have begin and end to be able to scan lists, and we've used this in this example to implement a C++ equivalent of the lapply function in R. We have actually another one that's better than this now, but this came fairly early on the project. So we grab a list from R, we grab a function, we create a new list of the same size, and then we just scan the input with the R function using std transform. Really easy. And it's sort of self-explanatory. Shidya?
This is from something that I've worked on the last couple of days or weeks. I got interested in taking an old, actually implemented in C optimization, not old, current package, but plain C optimization function where the user can send in a function. And this is what it would look like if you were to evaluate the vector of parameters par underscore given a function that maps from a vector to a real, to vector valued numeric to a single numeric in an environment row. With Rcpp, that's pretty straightforward. You just assign the numeric vector, you assign a function, you assign an environment, you then create a language object that's the function that combines the function and the parameters, and evaluate that in the given environment and return the scalar. But as I found this particular one, if you do that in the context of function evaluation, it may get called 10,000 times. There's a little bit of overhead in this, and these are just good exercises for us to find where bottlenecks sit, just as we did with the preceding example on the cumulative sums of the columns of the matrix, where at first we weren't actually faster than an already vectorized version in R. So this isn't as good, but if that's the case, oh shucks, we will get there. So I settled essentially for something like that, even though I was working with Rcpp and the rest of it. You can also just use the standard R functions. So there's lang2, which helps you a little with the Lisp headaches. Romain was kindly referring to on one of the earlier slides, the things you have to do for a function. And likewise, eval, both of these here prefixed with the rf underscore can be evaluated, and that's the same thing, which then is, when we're using Rcpp, the same as the, in speed and performance as the C version, because it really is the same. Other things that we're having, so this is a slide that details the aforementioned S conversion function. S is basically what you do at the input to your C function when you come from R. It's templated, so there's a template type T. It converts to an SEXP, and it's pretty feature rich. There's just about anything you may encounter now, sort of primitive C++ types. Recall again, this is for passage from C++, from R to your C++ context. So you're mapping into an in, double, bool, long, in any of the standard C++ types. Anything that already can be constructed with an X, anything that further specializes this template, or containers from the STL. We speak a little bit more about that in the extending vignette, because it has to do with some of the wrapping. The converse is then wrap, which goes the other way around. In goes the templated type T, out comes the S expression. That's what we would do at the end. It can, again, take any atomistic C++ type, int, double, bool, any SEXP, anything that further specializes the template, anything that has iterators and begin and end, as well as STL objects that use STL containers around the wrappable type. And there's plenty of examples now in the documentation in other places. Here's how you would use it, for example. Suppose that you had a vector of doubles, which we're just creating a type def shorthand here. So if then a vector z comes in, you can assign it to vac, just as before, the previous examples, int and doubles. You can also wrap them on the way back. And you can create relatively complex maps of string, of vector, by putting all of those together. So there's, yeah, two vectors and a scalar. Likewise, we have implicit conversion that works for environments, lists, functions. You can look up name from environment and lists, the way you would do it in scripting languages with, dictionary or hashes. Some of the expressions get by with implicit calls to wrap. That's sort of not really clearly demarked in the documentation. I find myself sort of that way, sort of trying sometimes, and then you get one of those fairly verbose compiler messages back, and then you have to put an explicit wrap there. So I'm not really sure how I would describe to how to use it. I mean, if in doubt, I most often just actually put a wrap around. With that, we have a few slides about the inline package that I started to refer to a lot in a couple of talks I gave on R and high performance computing, because it was a super useful package, and it later occurred to me, I was talking about inline and then I was talking about Rcpp, and I did that a couple of times, and then I realized, wait, I should stick those together. So I did a patch to it, and then later Romain did another patch to it, making it better still. This describes the way it's now in the current version after our two sets of changes. So now you have a function, CSX function, that extends the original C function by OLEG. What this does is it picks up an idea that I had first seen, I think, in the Perl world. Essentially, in your scripting language, you have what is a character string. It just so happens that inside that character string is a valid program in the language you want to use. This package then does the housekeeping. It sets this program body as well as any other management it needs around it, additional headers, makefiles, environment variables, puts it down on your operating system, calls the compiler for you, calls the linker, and loads it. It does this really, really cleverly, because once you know your R system and environment, there are things that you can take advantage of. Every R session is guaranteed to have a unique temp directory. That will get cleaned at the end. So it's really natural with that to write your temporary file in the temp directory, put your object file in there, load from that, because whatever else happens when this R session terminates, this will all be picked up. So it's literally as simple as it is there. So you can sit in your R shell, install inline, For the second example, you also need Rcpp because we use it, but I'll get to that in a second. For the first one, you don't need anything else but having a compiler on your system. So, that differentiates a little with say, the Windows users don't always have the tool chain. So what happens is, there's a bunch of arguments. We will see a few. You don't need that many. The first one always is signature. So you want to dynamically load a function, so you have to tell it what goes in. Here we're saying, I want to have something that's a variable named x in my program, and it'll be an int, and there will be a variable y that it'll be a numeric, so int and floats in C++. And what we're doing here, I mean, it's a trivial example. We're just returning a product so that I can have it in a simple line. That is the second argument to CXX function. It goes from the apostrophe to the other apostrophe. It's a character vector that gets passed down, and if you were to turn an additional optional argument verbose on with a value of 2, you would see the temporary source code that's being put out there. It's compiled, it's being loaded, and you get it back. And for simple programs like this, it just takes a second or two, because that's the time to write this mini function, compile and load it, and then you have a new function fx, because the result of CXX function gets assigned to fx, and you can call fx with an argument 2, which, was one of the newer R features we forced to be an int rather than cast up to a numeric, and a numeric 5. You can do the exact same thing now with something very clever that Romain came up with plugins that certain packages can then make use of and talk back. So Rcpp has a bit more in terms of requirements if you've looked at it, because Rcpp, if you want to build against it, it has headers. So now we have to tell the compiler where to find these headers so that it can happen. For the original program, all it did was using R headers, and you can inquire R about where those sit. That's always in the file tree. Now we have to do the same for Rcpp, and we have to provide a library too. So that's basically what plugin does, and what you then get in the simple example, and allow me, excuse me for stepping back from the mic for a second, it's just, instead of using plain old school macro API in C API, you now get the wrap as templated functions that we just talked about. And that does the same thing now with Rcpp. And it was there before us. We've just found it extremely useful. We use it extensively in the package, over 770 unit tests of last count. And many of the collaborators that we've now found since we went full force onto this, including John, do most of the prototyping this way. It's really quite nice. But even if you don't want to use our stuff, it's really neat for C, C++, and Fortran. And sometimes questions come up. So I have a friend in New York who's also in finance who puts a lot of trial and testing packages onto GitHub. And one of the things he recently played with was that he wanted to replace usage of bugs with something that's very popular in the Python world called PiMC. So he was doing a lot of Monte Carlo simulation with PiMC, and then he kind of figured, well, wait a second, can I do that with your stuff? What about templates? And we showed, yes, of course we can. And I quickly cooked up a simple example where a template type is defined and used. And we're basically doing the same thing here. And because it's a full program, I had to cut it short. But if I go back a slide, oopsie, this basically is the body argument to the function. So this is signature equal and then body equal if you were to write it out. An optional argument is inc for includes, which we're using here. So I have valid C++ code that just, goes to some other headers. He's on a Linux box, so those are being found. Amadeo we'll talk about later. CPP bugs is his program on GitHub. He really very much likes Boost, so he uses the Boost random number generators rather than ours or ours or Amadeo's even, and sets up his model and then goes on. And that's all he had to do. I haven't shown the core here, but it's public. He posted it to Rcpp Devel a little while ago, and with a really simple example, here's something that then ran circles around PiMC and bugs because it's just templated C++. What I should add is that he's a big fan of doing everything templated and having no libraries. So for him, just to also declare the include files was what was critical. So it really works as a framework. With that, we're now sort of closing inline, and we got a lot of the preliminaries out, and Romain will take it now and talk about something we added in the summer called Sugar.
Right. So Sugar comes from desires. So we spend a lot of time with C++, and we sort of liked the way we program in C++ and some of the benefits. But it turns out eventually that we miss a few things from the R language and the R syntax in general. So Sugar is an experiment to bring some of the R syntax back into C++ so that we can sort of have both of best of both worlds. So how did it all start? It started from a few questions on our mailing list about how to do certain things. And so this example there is again the same example I've shown before with a bit more care with missing values. So I essentially want to scan a numeric vector and do something with it. It's all nice. I mean, it's really sort of pedestrian C++ coding exercise. There's nothing wrong about this. But we sort of missed the R syntax, the R way to do it. If we want to express that kind of code in R, you would just do if-else x lower than y, then x times x, or minus y times y. Obviously, this is a really silly example, but anyway. So what we do with Sugar is that we bring if-else back into C++ so that the function you write is essentially the same as the one in R. So we grab numeric vectors so that we have object of the appropriate class, and then the expression is exactly the same as in the R expression. And we have a lot of feedback, and people really enjoy using this. Some other example, using R for so many years, people love to use lapply or sapply or things like this. And now we can use them in C++. So assume you have a really complicated function there called square that takes a double and squares it. Many years of engineering in C++ to come up with this one. You then can sapply this function directly in C++. So you grab the numeric vector and then you say sapply x square, and then it'll do it for you. And so, some of the magic we've put there is that if the function was returning, I don't know, something else, for example, a numeric vector, instead of you would get exactly the same behavior as you would get in R, so that it would create a list of numeric vector for you. And all of that's happening at compiler time thanks to template metaprogramming and things like this. So what's in the Sugar box? We have logical operators. Is a vector lower than another vector, greater, different, equals. We obviously have arithmetic. And we have many functions that we are borrowing from R. We obviously can't bring everything, but we're quite confident that we bring a sufficient subset to be able to do some things. And people are getting happy with this. So, rep or pow or min, lapply, sapply, these functions really allow you to write concise code in C++. Functions to operate on matrices, so outer, col, row, the lower triangle of a matrix, and so on. And, lately, with tremendous help from Doug Bates, we've added all of the statistical functions, R norm, D norm, Q norm, P norm, and so on for every distribution that's in R. But these functions are now C++ functions, and that allows us to embed a few optimizations also in them. You'll find much more information on the Rcpp Sugar vignette, because we can't cover everything in one presentation. And I wanted to close the sugar part with a few benchmarks of this. So it's all very nice to have nice syntax, but if we have to pay the price somewhere else, then it's not interesting. So what we wanted to see here is that, does it actually work? Is it faster than the R version, and so on? So we tested this with a few expressions, and well, we've introduced a bit of bias there, but whatever. So the first expression, you'll see quite an enormous benefit there, where the sugar version is about 10,000 times faster than the R version, and I can explain you why in a second. Then if-else, which works about 15 to 20 times faster, depending on the information we embed. With one version we have, we can embed in the expression the fact that the vector does not contain any missing value, and this allows us to calculate the product or any other expression faster. And then sapply, as you can see there, without the overhead of the R interpreter, can get much faster. Now, why do we get such huge benefits on the first one? That what essentially happens is that the evaluation goes lazy. So in R, if we had to evaluate any x times y lower than 0, what would have to happen is that we would have to calculate x times y, allocate new data for this whole vector, and then we'll have to allocate another logical vector to host is x times y lower than 0, and then we scan this. In C++, we do it totally differently. With compile time, we're allowed to compare the first x times the first y with 0, and if this is already true, then we can stop there. There's nothing more to do. So this is why in this example we get so much faster, because there's no extra memory allocated, and the first true condition, this is where the bias was sort of introduced by us, is really early in the vectors. So this is why we get such improvements. Some of the benchmarks there, in the writing R extension, there's a notorious example about convolution. And so in a forthcoming, well, hopefully, paper in the R journal, we've came up with an Rcpp version of the convolution, and we wanted to see whether we could do better than the usual example. And it turns out that we can make a version that's about a third faster than the benchmark. So we're quite thrilled about this.
That covered a lot of RCPP. There's two more extension modules that Romain will talk to towards the end, and I hope we'll have enough time to do that. But I want to break a little and talk a bit about RInside. That was something that we also had on the title page. So this is something completely different with Monty Python. I've been with R about a decade, and every couple of years someone came up and sort of said, well, we should really have something for shebang scripting, because, with R you could do R command batch or redirecting. Those are all crutches. It's all awful. At some point, maybe around R16 or 17, there was someone from R&D in Detroit. At the time, they still had R&D, I think, who had a patch that did something to the engine. I think Duncan Temperleng also had something, but sort of it never happened. I asked that guy, he sent me that patch, I never really looked at it. It then so happened that a friend at Vanderbilt, Jeff Horner, had learned a lot about embedding R for using R Apache, which was a wonderful product that he authored. And I think in response to yet another email about that, with the shebang, started doing something. And By that time, I'd learned sort of some tricks just about the ropes with configure and other things, so I helped him. We started working on this together. That led to Littler. So Littler then, that's the one time in my life that I was a little faster and sooner out with something that worked than Brian Ridley. Brian Ridley, being ultra competitive, will never admit to that. Littler is now shadowed by RScript. But we were there. It works. It still has sort of some advantages to the internal. So long story short, Littler embeds R. It's sort of a shebang piping front end. It's really, really good. You guys will like it on large systems. I used it a lot for some of the HPC exercises. And doing that, what it does there is it just runs through R files, picks them up line by line, sends them to the interpreter. So then I kind of figured, that would be useful. And I needed something like that for just backtesting operations that I was doing at a time that I had data that I accumulated in C++ programs, and I wanted to do R over it. And what you then commonly do is that, you cook something up that writes out a CSV file, you call R, you bring the results back in. It all works. It's all very pedestrian. It's really boring. You have no aura control, and it doesn't perform well. So I kind of figured, wait, what Littler does is exactly what I should do for a really simple exercise in creating a class that embeds R. All the functionality is there thanks to Arco about how to embed it. And then we did that, and that's so I released that a while ago, and that, because it interfaces between R and C++, also got a lot better now with Rcpp. It's a nice little package. Now we're co-authors on it, and there's this tremendous number of examples in the package. It's pretty straightforward, and sort of this is what it does. You instantiate an object RInside, you give it argc and argv. That's it. You now have an R interpreter in your C++ program. And thanks to Rcpp and the explicit and implicit wrapping, sending things back and forth is a lot easier. I had something relatively pedestrian, now we have something high-end. So just how we showed example earlier for the environments, you can just assign. You just have a key value lookup, you have an hashed object text in the R interpreter that gets assigned. And it's the R semantics on the other side that find the proper type to it, because we sent a string to it. It's it's a character in R behind it. And then the basic hook to get everything out is pass eval or pass eval q for quiet. That doesn't return anything. So if I just want to say hello world, well, that's my 3 lines of hello world. So that's, the silliest hello world the two of us could come up with. So it doesn't do a hell of a lot, but it shows you already what it can do. Other examples are that, you can assign 2 numbers, evaluate an expression, and get the result out and point it in. So it goes really easily bidirectional. This is something I don't want to spend too much time on it. That was sort of one of those, oh my God, why are they doing this way? There was someone on either RDevel or maybe on the ASIC finance list that I'd share who wanted to do something that had to do with standard finance, using one of the wonderful metrics packages, basically just calculate something on a portfolio under constraint. You see it here thanks to the beauty of highlighting in red. I don't want to get into the detail, but he was trying basically to milk R computations from a standalone C++ program, but he had great difficulties there. He kept emailing for weeks, and then one evening I just cooked that up, and it became sample 4 in RInside. The edited there in brackets just means I had to sort of shorten something to fit it on the page, but otherwise the same example, and it works. If there's R functionality in packages you want to load, you just load the package. Library F portfolio, and off you go and you use it. So if you have internal or external packages, they're available now to your C++ program. Last example we added, it relates to the embedding. Suppose you have a a highly performing C++ function about as powerful as a square example that we had earlier. So this one takes hello and concatenates a given string to it, just to show you this is a standard C plus equal, couldn't do that in C, function. We can now assign that to an operator in R, to a value in R. So that function, because we take the function pointer, that function, assign it to an R object hello, and then just pass an eval hello world. So we're calling the hello function with the payload of world. We're asking, well, what does hello and world give? And, answers are due at the end of class. Just kidding. Obviously, it tells you hello world. So even in the embedding, you get back to basic C++. It's nice. But you know, one of the greatest things about open source is that every now and then you put yourself out there on a shingle and wonder whether people find it, use it, extend it, and then sometimes people come back. So Jianping Hua, I hope I pronounced that right, is I think at U of Arizona, last winter sent me something back that made me just go, wow, that is really clever. So what had she done? She'd just taken your basic MPI Hello World example and used that together with RInside. So now you're in the environment of, say, autorun for the OpenMPI environment. You spawn a large number of C++ programs, and lo and behold, they all have RInside. Now you're taking the advantage of R, well, advantage, that it's single-threaded, doesn't have many large requirements, is the way we dimension system these days, a reasonably small application, and you just throw it out to 1,000 nodes. And each of those, thanks to the magic of MPI, just works. So you get, 20 years of R, truth and test, and it just works. And you get, 25 years of MPI, they work together, and it just works. I haven't really had a chance to really crank this, but this is tremendously clever. And we take no credit for it. I think I reworked it a little. I think she sent that as an MPI example with the C API, and then I kind of just figured, oh, well, I may as well make it C++ API. That's how 2 examples became 4. So why is RInside interesting? You may have C++ programs that compute, gather, or aggregate data. Go figure. I mean, that's what we write C++ programs for. Do something with data. So you have data. So then you want to program with data. So you want to benefit from R, because you need to, save and analyze your data, and you may have to do that, in the cycle. You don't want to dump it out to files. So with RInside, we can now skip this dumping and launching and what have you step. We just collect our data. In the beginning, I was just using STL vectors or STL vectors to approximate matrices because I had nothing better with little time. We can send those to R very easily thanks to the Rcpp wrappers, as and wrap and all that. Have short, simple R expressions. Maybe they load another package. Maybe they source another file. You have it encoded somewhere. Evaluate and get the results back, and it just works like that. We shipped 9 examples in the standard subdirectory of examples, and 4 sort of 2 by 2 for MPI with that. So that's a really short run through for R. Let me do that, and then I give it to you for objects. Protobuf. This is sort of really funny because, as Romain alluded to, this is how we got started with this, and that is, what are we now? Yeah, October. It's just about a year ago, and if I could milk this power that I have to transform lives, you'd see me on late night TV, because I sort of suggested to Romain, well, you want to learn some C++, read these Myers books, and weeks later he comes back and does wonders with it. If only knew how I did that. Now I stand here and explain protobuffers to you guys, so I don't really have to. So, I often refer to it as, binary, better, faster XML. Hence, our example with those icebergs, these glacial, large, horrible icebergs are XML to us. So now we have protobuf. We describe data structures, and code gets generated for us. Wonderful. So there's a really simple proto definition. You get the C++ code from your standard documentation for protobuf, and on the right you get what we can do with that. It's really sort of quite an achievement, because we almost have full introspection inside of C++ now because of the way Rcpp, the object model, the RProtobuf library all interact. There's no code generation and compiling and linking going on. That's what my very basic first example did. What we're doing now is proto files get analyzed, and the rest of it just flows. It's quite impressive. There's the second example, but we have 28 minutes left. I'll just skip that. And oh, sorry, I meant to take this one too, and then I'll pass it to Romain. So one of the things that I'd done then with Rcpp was, how can we do things faster? I grew up as an econometrician. Econometricians often write papers by doing Monte Carlo simulations of small sample properties. You want estimators as well as the estimated standard errors. R has a couple of really fast functions to do linear models, OLS, estimation quickly, but for the fast ones, you don't necessarily get the standard errors back. So we figured, okay, what can we do to do that really quickly? This was the first version Again, this is all it takes, thanks to inline. I guess we're still using CPP function there rather than CXX function. What happens is we're getting some numeric vectors. That's a typo. That should be. Oh no! Well, it's a really old code. So then we still use the numeric. We call it numeric vector. We call it embed matrix. So don't want to stick here too long. There's some passage going on into our data structure over to Armadillo data structures. Armadillo is a maybe 2-year-old lovely project out of NICTA, or maybe they call it NICTA, which is sort of a government-sponsored research organization in Australia. Really clever, heavily templated linear algebra stuff with really clever benchmark examples how it outperforms other C++ implementations. So it's a bit like Blitz++, which no longer lives, and is a bit better, I find, than the Boost linear algebra stuff. So we use something like that. We started working with that and then created a little bit of glue, so we can do better than sort of the basic example. Now there's a package Rcpp Armadillo, which basically sends our types through efficiently. So we're using constructors for ARMA, which basically take a memory pointer, the dimension, and a false Boolean saying that don't do a copy, just pass it through, trust us, this object has n by k dimension, work with it, and then estimating your linear model is nothing more than solve x given y. So that in our lingo fits y tell the x. Then you're calculating residuals. We're calculating S square really quickly, and with that can return the coefficient, the standard error, and the degrees of freedom. That was motivated once by a question where someone wanted to do something really, really quickly. We started doing it with ARMA. In the HPC tutorials, I did it with ARMA, and before that with GSL as well. Given the time constraint, I won't stay here for too long. This is sort of a half-finished package that we have on RForge that this takes the sort of the wrapping, the glue, the access to other given data structures to GSL, which a lot of people use. Unfortunately, it's not as slick as ARMA because it can't be, because the underlying data structures are C and not C++. So, but we still want to get back and finish it eventually. But I'm not going to say much about it. That was basically just 3 fast examples for, say you want to run a million gazillion linear models and you want to do it fast. These are choices that you have. The best one for that definitely is FastLM now in the Armadillo package.
Okay, so we have about 20 minutes to finish now. So I'll go fairly quickly through this. The idea was to give a short review of how do you do objects in R, and so using this as a sort of a thread to link to new developments we've put in Rcpp recently with John's help. So I'll go quickly because some of this material you probably already know a fair bit about. So there's many ways in R to come up with ways to represent objects, and you'll see the list there with pencils. So I'll quickly go through them. The thread I'll use there is a fairly sort of old example, which is the bank account example. A fairly, well, really schematic view of a bank account is the balance you have on your account and perhaps the authorized overdraft. And then what you want to do with the account is you want to open it, check the balance, put some money on it, get some money out of it, and so on. So the first way to sort of do this comes from a demo that's in our demo scoping. Uses a feature that's perhaps not as known as it should be in R. For me, it's one of the best features of the R language, the lexical scoping. It works. It essentially works because you define a function within another function, and the way objects are being looked up. If an object is not found in the environment of this function you're creating, it looks up in the other enclosing function, and so on. And this simple mechanism lets you encapsulate data in a really simple way, which there. So, for example, in the deposit, you query and set total there in the enclosing environment. But the actual account you create after that does not let you easily modify the total variable, but you get access to it through the elements of the list you return, and this is fairly nice. There's a few sort of small problems with it, and we'll maybe cover this. So on top of that, there's S3 classes, which I hope I'm not saying anything sort of stupid here. But so S3 was the sort of first object-oriented way of representing data. Any object in R can become an S3 object. The only thing you have to do is assign the class attribute to it. And for that reason, it's really easy. You just grab an object, give a class, and that's it. But for that reason, it's really also very dangerous, because you cannot just grab any sort of garbage from anywhere and say that's a GLM or that's a LM or that's a density fit or whatever. So there's no restriction there, and this is why it's really dangerous. But it gets the work done. So how do you do this? As I said, you just assign a class to your object, and then it works with generic functions and implementation of these generic functions that are called methods and so on. So the balance generic function there, you recognize it generic because it calls use method, and then the implementation of balance for the particular S3 class is given there. So I'm going really quickly on this, but anyway, so other functions as well, so little checking of consistency of arguments and so on. And then you would use this like this. So you create an account, check the balance, put money on it, withdraw money from it. The only thing I'd like to highlight probably there is that because of the way data is being passed, if you modify the object, you have to grab the result from it. If I cycle back there, you see that I do $X balance equals $X balance plus something. Well, that actually creates a new X, right? Right. and so you need to grab this new X, because it'll be different than the. So for example, I'm passing myself to the deposit function, and the result I'm getting, that's not the same object. And it's nice enough. I mean, if you want to create, for example, a GLM and then do something from it, S3 is nice enough, but once you really start to want to do object, OOP, then probably you want something else, right? So S4 classes, I'll go even faster on this. It gives you much more control of your classes. So you have formal definition of the class. You are able to embed validity, so that you're able to define if this object is valid. And dispatch is much more powerful. But I mean, I don't want to be insulting or anything, but it's a system that requires to write a lot of code and more annoyingly, a lot of documentation. I mean, there are helpers that are nice, but when you start writing a substantial package using S4, you end up writing tons and tons of documentation. And well, people like this, people don't like this. I'll let you choose your side. Anyway, so yeah, the class is more formally defined. So you define the class, you define the slots of the object. So the balance is a numeric vector, the authorized overdraft is a numeric vector. You're able to give a prototype of the object, and then the validity function there. And then it's about the same thing as S3 in respect that you define generic function and implementation of these generic. Well, you can go much further than S3 because you can do multiple dispatch and things like this. But the idea is the same, that it's the verb that controls everything. You don't say object. You don't invoke a method of an object, but you invoke a generic function, and you get dispatch from, yeah. Anyway, so the syntax is a bit different. But then once you have done all of this, you use them about the same way. So fairly recently appeared reference classes, which some of us call R5. It's not the official name, but we're trying to get John to agree on this name. Anyway, the way I see them, R5, well, reference classes let you have both advantages of S4 and of something simple as lexical scoping. They are real actual classes, but, you know, which implies formalism and dispatch and all the rest of it. Quite a bit of documentation, but not as much as S4, at the moment, at least. Maybe John will change his mind, I don't know. But the real interesting thing is that these objects are passed by reference, which is quite different than whatever else I presented before. And this is really easy to use. So the way you would create a new reference class is about similar to, it's a bit between S4 and lexical scoping way of doing things. So you give a name to the class and give the a definition of the fields. So and the fields is really what differs from S4. In S4 you call them slots, and those are passed by value. In reference classes they're called fields, and this is what is passed by reference. So the balance and the overdraft and so on. And then the other argument is the methods. So here I'm defining two methods, withdraw and deposit. This doesn't appear there, but one really nice thing about this is that one method can call another method, and well, this also has inheritance and everything. I mean, this was just a quick view of it. If you're interested in learning more about this just came out in 2.12. Just go * reference classes and really encourage people to have a look at this. Right, so once you create a new object there using the generator, then it starts to look more like usual OOP systems. You do object $. We cannot do dot because we cannot. But anyway, we do $. So object $method and then parameters of the method. And as I said before, those are passed by reference. So if I were to create a borrow function so that Dirk can borrow maybe not money but perhaps time from me, I'd go like this. So what the borrow function would do is that withdraw money from one account to deposit on some other account. And what I wanted to show there is that since objects are passed by reference, they are modified in place. So you don't have to grab the result of the function so to make sure that you're still in sync. Your object is really a reference. That changes a lot of things. You could do it differently. You could dynamically add a method to the reference class by calling the methods function of the generator there. That's another way to do it. Much more documentation to read on the question mark reference classes in R 2.12. Anyway, so going further, what we want to do is, rather than use R object, we perhaps want to use C++ classes directly in R. And for that we came up with something we call Rcpp modules. That's inspired from another library called Boost Python that does something similar for C++ and Python. So we want to expose this fairly simple C++ class so that people can use it directly in R. So the class itself is sort of self-explanatory, and well, that's the same example we've seen all along. So what if we want to expose this to the R level? All we have to do is write this piece of declarative code there. So we create a module using the Rcpp module macro there, of which we give a name, Yada. I hope the Seinfeld fan would appreciate the reference. And then we essentially say that we expose through the template argument the account class, and then the argument of the constructor of class underscore is the name we want to give to this class on the R side. And then we declare what field and what methods we want to expose to the R side. So we want to expose a read-only field balance. So we give the name balance and we give the pointer of the C++ field. And similarly for the methods, we give the name we want to use on the R side for the method and the method pointer. Right, once this is done, compiled and everything, we can directly use this on the R side. So we grab a count from the module. Well, Yada is the module. The module will let you expose either C++ functions or C++ classes. We might have to skip this later. Then we create a new account, deposit money, withdraw money, check the balance. Everything there. The only thing that's on the R side is really a pointer to the data structure that lives on the C++ side. There's nothing else on the R side, and all of this sits on top of reference classes that have been introduced in R 2.12. Yep. So that's a quick way to. Obviously, this example is really sort of simple and stupid, but if you had a fairly complex C++ class and you didn't want to manage this in R directly, but just do a few operations on the instances of this class, then modules lets you do this quite efficiently. Well, we already covered this, but another way perhaps to do objects protocol buffers. It's not totally appropriate for object because protocol buffers really dumb data structures that you cannot associate methods to them, but as a quick way to encapsulate a certain type of data, that's possible. Right, there was a bit of a few slides on directly modules, but I'll really go quickly on them. So as I said before, modules lets you expose C++ functions and classes back to R. So again, the most engineered function of the of the slideshow. Hello. So as you can see there, there's nothing R related in this function. There's no macro, there's no sexp, there's no even RCPP thing. It's just a function that takes a string reference and sends back a C string. And I want to expose this back to R, so I want to use this function in R. And module lets you do this quite easily. The only thing you have to do is declare that you want to use it. So you go function, give the name of the function, and give the function pointer there. And then you're just able to use the function by grabbing the reference of the module and call the function. And obviously there's a lot of type checking and everything to make sure that you're not passing something that's not appropriate for this particular function. Exposing classes, I've covered this already, so I'll skip. Do you want to finish up with this? And you have 2 minutes.
So getting towards the end, so we just thought we hadn't really said how you use this in your package, other than pointing the fact that among the 8 vignettes included in the RCPP package, vignette is a sort of self-contained PDF document, is one RCP package that has details, but one really nice trick is to prototype using inline, which we advertised earlier. It really works quite well. And then the object returned by CXX function, the function that you can call, it has a lot of baggage behind the scenes about how it was being built, which we can then pick up, or which package skeleton picks up to basically generate yourself a package out of it. So you use inline, you call package skeleton on the generated function, and magic happens, as with Disney. Sort of kidding inside, the thing that happens is that we overloaded package skeleton and made that do stuff for us. So, but as it then goes, as we were debugging that in the hotel this morning, actually turns out that it got a hiccup with the single one, so that's a good excuse to show you CXX function for several functions at the time. These are now once again nonsensical, but the nice thing, and that goes back I think to earlier versions of C function, is that it generalizes to lists of everything. So if you just want to generate several functions, instead of passing in a signature and a function body, you just pass in a list of signatures and a list of function bodies. These are named lists, so we're creating tick and tag, and between signatures and bodies, the names have both to be present or it just returns empty. So you want to do it this way. So this is a real life example. We ran this. So this then generates you foo, which has a function tick and a function tag as defined there by the code. You can test them. I was doing some simple sort of distant measure-like things. Ignore the computing that it does. But if you now want to create a package, all you do is call package skeleton with the name of an R package you want to create. And the way package skeleton generally works is you pass it a list of R objects that should be in the package. And in this case, we just give it foo. I guess as the code is in the repo as of today, it wants lists there. So now you have a package that generates 2 functions. That's really all there is. Bit of further reading in case this sort of whetted your appetite. The package, as I mentioned, has 8 vignettes. The first one is an introduction that's reasonably full-featured, now revised and resubmitted and hopefully forthcoming. It's self-contained and current thanks to the review process. We also have an FAQ document for a couple of things that have come up on the mailing list. We tell you how to use it in your own package, as I just did. There's a document that talks a little about the glue that we use for Amadio and GSL wraps. Then we have 3 further vignettes that are in a half-baked state that isn't fully finished, sort of one on sugar, one on modules, which still changes a lot. We borrowed sort of something from other FSF documents. We want a quick ref that just shows you the API, but there's so much there, we haven't written that one either. And always generated, that's an idea I think we got from some other packages, is there's unit tests in the package, and our unit test then shows you the result of all of them. The unit tests generally also double up as hard to read documentation. Sort of kidding aside, we try to stress every relevant fact. So if you think about can you do this or that, that's unfortunately what we do ourselves every now and then. We just grab among those. So that's sort of there. RCPP is being picked up. There are now 15 packages on CRAN, including our CRAN and bioconductor. Some of those are our own, but not too many. There are a couple of other people who we didn't coerce to use our stuff, and they still do. And then there's the mailing list, which is also growing and has archives. And with that, we're sort of at the end. This is a final slide from one of the other presentations given this year. So if you want, paid support for that, I think Romain would be happy to help. I do have a job, so I don't really offer that. But again, thanks for having us. We're happy to take questions now and or later. Oh, yes, and microphone was recommended so that it gets recorded.
Yeah, so this may be a question that's a little premature given the rapid pace at which you guys are doing things, but trying to play around a bit with this lately. What I've been doing is to look at pieces of C++ code, particularly pieces of C++ code that are already interfaced to R, which of course biases it. And what I tend to see is often interesting stuff, but of course, it's very C++ oriented. And so to take one example, which apparently isn't too popular around here, the Boost library for dealing with graph structures. It's very nice. But internally, and even in terms of its interface, it's very C++. So the challenge then is how do you go about taking something like that and presumably adding something to it that then makes it compatible with something like module or even somewhat lower level RCPP code, and ends up with something with a few hooks that an R programmer can deal with. Now, in the existing code, of course, this is done by pages and pages of C code and pages of R code. You guys have a way of, I think, getting around a lot of that, but it's getting from here to there seems still to be quite difficult.
Yeah, that's a great and relevant question. I mean, I recall that I think in Soda you also review the GBM code, which is sort of pretty nice C++ code that all existed, even though it had to do protect and uppercase macros and all the uglinesses. But Greg did ages ago. It's really good code. Thorsten Hothorn has some fantastic code, for his tree-based stuff. It's all C++. That's sort of there. We haven't really thought about Boost. We did think about Qt. I like Qt, and Depian and Michael have done a lot of work sort of redoing some of the graphical infrastructure that's say in Gigobi and have possibly answers to finally having dynamic graphics devices in R and sort of all that. It's it's not clear, because if there's a lot of baggage and a lot of head splitting and a lot of trips for Romain to the pharmacy to get more Valium and Tylenol, then it's not clear, because at the end of the day, you may remember this, that back when Borland was still sort of a market-reigning compiler, I think the expression was that there's 5 people on the planet who can write a C++ compiler, and the language is there. I sometimes joke that the language now is no longer the language I learned 20 years ago, which is why I'm back using it, because it's rich and it's changing. But Myers calls it sort of 4 different facets. There's so many different ones to support that, going out boldly and claiming that you can do all of them, we can't. I mean, we sort of do that part-time here. So, I mean, it's just, it's a great initiative, and I think it should get tackled, but we may need a plan and help. I think it's sort of doable, but some of the stuff, Boost is a good example. It's fantastic. It's rich. It's peer-reviewed. It's fast, but lots of interdependencies and lots of, coding baggage and intricacies, which you can't really with a scalpel take out. So it's great question, great challenge. Maybe we'll meet it. I don't know yet.
I don't really have much to add to what Dirk said, but the what tends to happen is that we've done this with a few libraries, as we've shown. We've done Armadillo, we've done GSL, sort of making wrappers around these libraries so that so that they sort of talk to RCPP and then talk to R. there's no real recipe, and every time we do it, it sort of change what we do in our CPP itself, and we try to embed this information in a vignette, but with a new library, you'll have different challenges, and there's no real recipe there. This is sort of what I had to say about this. Anyone else? Or John again?
So I think there's some chance I might repeat John's question, but I want to repeat it in a different context, and maybe it's a different question, I don't know. So let's suppose I've got a C++ library, and I've got an object, and we can call it a foo, or we can call it maybe a capital M model, right? And I've got another object, and it's capital D data, right? And maybe these are abstract classes or something, or maybe there's actual instantiations of them in concrete classes. If I use your objects framework and instantiate a model, kind of Swigit or whatever, Boost Python it into R, and then I have a data, can the R version of the model construct itself using the R version of the data? Do the different do you have to assume that all these things are freestanding things and they're only going to operate on ints and doubles, or once you've instantiated two different things that play together nicely in C++, do they continue to play together nicely once they're in R?
Well, there really is nothing in the R side. The R side only holds a pointer to the internal data structure, so I'd have to say yes. Yes, it would work. Yes, it would work. Yes, definitely. Obviously, I didn't try it on this particular example, so my word is as good as no. But I'd have to say that yes, it would work, because what's on the R side is really just plumbing to let you access methods and fields. So yeah, you only really have a pointer. So I don't know if you.
No, I fully agree. I think for as long as it's compilable and linkable, it happens, because that just means that the units combusting the C++ code generate what it's needed to run it. The way this started a long time ago was I used to call this sort of vertical. I had a prompt in R and I wanted to get something done that wasn't C++, so I just wrote accessors and returners. And we're much richer now, and I sometimes call that horizontal. It's not the greatest metaphor, but now it sort of goes this way, and that's sort of where you're coming. Can you sort of come in here somewhere and come out on the other side? And at the end of the day, we're still building, a single program. So if something allows us to compile and link this together, then it should be resolvable.